Hello, my dear NEET warriors. Welcome to the Vedantu NEET English channel. This is your Captain Shreyas, your physics master teacher. And we have this amazing team of your NEET warriors. Veet Baswa Sir, Gopika ma'am, your Diksha ma'am, and of course me, your captain. And we are all, active on our Telegram channel. Before we begin the class, let me just tell you that we will be conducting weekly mock tests, free of cost. Daily quizzes, weekly sessions are there where we interact. There are comments which you can put up. Also, you'll get PDFs and also the Super 6 series and any other updates that come up for your NEET. So make sure you're a part of the NEET English Telegram. So today's topic is all about thermal physics. So what are we going to do? Well, in thermal physics, we're going to start off with what is temperature and temperature scales and their conversion. Then we will go to thermal expansion, apparent expansion, thermal stress, pendulum clocks changing their time period because of temperature, all these things. And after that, we'll be doing specific heat capacities and latent heat and calorimeter, where we'll be seeing what happens when you mix liquids and all those stuff, right? So calorimeter based questions as well. So that's the agenda for today. And we are going to solve NCERT questions as well as PYQs. So make sure you are tuned in onto the channel by hitting the subscribe and smashing the like by showing your support. Nice to see all of you. Hello Krishna, hello Sinai, hello Hasni. Good evening, nice to see all of you. I hope you guys had your dinner. Hello Subhag, happy evening too. Alekya, nice to see you back over here. Hi crazy dude. Hello Babi, hello Krishna. Thank you for trending WP as well. Yes Teju, thank you so much. I'm very good. I hope you guys are doing great. And please call your friends that what are you guys doing? Shreyas Sir is live. Come on, let's attend his class. Okay, starting off with temperature. Okay, so what is temperature? Right? Temperature, if you remember from your lower grades, you will remember that it is nothing but the degree of hotness or coldness. Yes, in a way it is right. It's the degree of hotness and coldness. But a proper way of writing temperature, we have seen that in KTG also. Temperature, strictly speaking, temperature is a measure of average kinetic energy of molecules, right? That's what it tells me. If the molecules have more kinetic energy, they are moving more rapidly, it has more temperature. If the molecules are very cold, that means they are hardly moving, they are hardly colliding, they are hardly having any kinetic energy. So that is cold. Hot means they are vibrating, they are shaking, they are twisting, they are moving, they are rotating, all sorts of things. It's a scalar quantity. SI unit is Kelvin. The other units are Celsius and Fahrenheit. So how do I convert from one to the other? We'll be conducting the class for 1.5 hours to 2 hours, not more than that. Well, simple. Celsius to Kelvin is the most easiest. If you have 0 degrees Celsius, that is 273 Kelvin. We all know that. So whatever you have in degrees Celsius, if you add 273 to it, then what you get is Kelvin. Then what you get is basically Kelvin. Similarly, what about Celsius Fahrenheit? You might have heard the temperature, this person is having 100 degrees temperature. He is hot, that means he has fever. 102 means very severe fever. 98, close to 98 is normal body temperature. So how do I convert from Celsius to Fahrenheit and Fahrenheit to Celsius? The logic is very simple. See, what you do is, say for example, you have been given in degree centigrade. What you do is you first of all subtract 32 from it. First of all, subtract what? 32 from it. Why 32 from it? Why 32 from it? Come on, my dear warriors. Do you know there is some temperature? Okay. Do you know at 32 degrees Celsius what exactly happens in Fahrenheit? Do you know that? Just one second. Let me just drink some water. Just one second. Okay. Yes. Hello, hello, hello. Yes. Welcome aboard. Welcome aboard. Welcome aboard. Yes. So we are discussing Celsius to Fahrenheit conversion. Yeah. So I was asking, there is some special number 32, and in Celsius and Fahrenheit, it plays a very important role. So remember this very simple thing, that your 0 degree Celsius is basically 32 Fahrenheit. 32 degree Fahrenheit. Just keep that in mind. Yes, I think Alekhya has said it. Very nice, very nice. So 0 degree Celsius is 32 degree Fahrenheit. So in fact, over here, if I want to convert from Celsius to Fahrenheit, I will just put plus 32 over here if I'm going from Celsius to Fahrenheit. Because if I put the value of Celsius as 0, adding 32 will give me that Fahrenheit. But before doing that, there is one number with which you need to multiply it. There is one number with which you need to multiply it. And that number, my dear warriors, is nothing but 9 by 5. 9 by 5. When you multiply degree Celsius with 9 by 5 and then add 32 to it, then what you get is the temperature in degree Fahrenheit. So remember, 0 degree Celsius is nothing but 32 degree Fahrenheit. 0 degree Celsius, the freezing point of water, is nothing but 32 degree Fahrenheit. If you remember that and that number 9 by 5, you can easily convert from one scale to the other scale. Very nice. Now, if you get confused between 5 by 9 or 9 by 5, how do you remember it? Well, I'll tell you. Out of Celsius and Fahrenheit, who is more sensitive? Meaning, when you change the temperature, where the value changes more? The answer to that is Fahrenheit. And that's the reason why doctors use Fahrenheit to measure a person's temperature and not Celsius. Because when you have fever, your body temperature might go from 37 to 37.5 maybe. So you'll be like, 37.5, almost same. But in Fahrenheit, that 98 might show 99.5, 99.9. It will show more value. Then you'll be like, oh, he's got 99.9. That means maybe he has fever. So that's the reason why Fahrenheit scale is used to check if somebody has fever. That means Fahrenheit is more sensitive. So that's why when you go from Celsius to Fahrenheit, you multiply by a number more than 1. 9 by 5. 9 is more than 5. So when you multiply it by a number more than 1, automatically it becomes more sensitive. Understood? Is that clear, my dear students? Everybody with me? Okay. So keep all these things in mind. How do you convert from one scale to the other? Now, the Celsius scale and the Fahrenheit scale show different readings for many temperatures. Except there is one reading when both of them show the same value. Like 0 in Celsius is 32 in Fahrenheit. Maybe 98 Fahrenheit is close to 37 degrees. The values are different. 98, 37, 0, 32. Is there some value for which they both are having the same value? Is there some value in both the scales where both of them are same? Answer is yes. So first of all, write the conversion formula. Degree Fahrenheit is 9 by 5 times degree centigrade plus 32. Correct? So let's assume the same values which are similar is basically x. So therefore, x is equal to 9 by 5 times of x plus 32. 9 by 5x plus 32. Now rearrange. Shift 9 by 5x over there. So x minus 9x by 5 will be nothing but 32. Take the LCM. Won't it become minus 4x by 5? Minus 4x by 5, because 5x minus 9x is minus 4x by 5 is basically 32. 4 cancels. It will become minus x by 5 is equal to 8. So what will x be? 8 5s are 40. Shift the minus sign. What it means is minus 40 degree centigrade is minus 40 degree Fahrenheit. Both are equal. So the answer is minus 40. Is that clear? Everybody with me? Cool. So this is one value which you can remember. Direct questions may come in the NEET examination. Now there is one peculiar question which can come in the NEET exam, which is very different from these formulas. These are known scales: Kelvin, Fahrenheit, Celsius. You know how to convert from one to other. But what if you have unknown scale? What if you have a completely unknown scale? Maybe we call it the Pandu scale. Pandu scale of measuring the temperature. Pandu says the water freezes. Pandu says the water freezes at 10 degree Pandu. And he says the water boils. Pandu can say anything, right? So he says, Pandu says the water boils at 200 and let's say 10 degree Pandus. 210 degree Pandus. That is what Pandu is saying. Champa says something else. This is Champa scale. Champa says water freezes at minus 20 degree Champa. This is not Celsius, this is Champa. And then she says the water boils at 30 degree Champa. Some random value she has taken. Now, how do I establish a conversion factor between them? Or what if a question is, if Pandu says the current temperature is, if Pandu says, let's say for example, Pandu says the current, let's say the temperature is, something like maybe 110 degree Pandu. Something like 110 degree Pandu. Then what is the temperature which Champa will show? What is the temperature which Champa will show? Right? So how do you solve these kind of questions? In order to solve these kind of questions, I'll teach you a simple trick. All you draw is two axes, x-axis and y-axis. One scale here, one scale here. Two scales are there. And just imagine one straight line going like this. Imagine 2 points on it. Point number 1, point number 2. Point number 1 has some coordinates. I will call it x1, y1. Point number 2 has some coordinates x2 and y2. Then any random point on this which has coordinate x, y can be written down in something called as the 2-point slope form. It looks something like this. x2 minus x1, or I can just start with y first. y2 minus y1 upon x2 minus x1. Same thing, minus y1 minus x1. But here you put y and you put x. That's the only difference. y2 minus y1. y2 minus y1 upon x2 minus x1 is y minus y1 upon x minus x1. This formula you can directly use. So in our Pandu and Champa problem, in our Pandu and Champa scale problem, can you similarly visualize this? If I put Pandu scale here and Champa scale over here, Pandu scale over here and Champa scale over here, think what will happen? Pandu scale over here and Champa scale over here. Pandu says 10 and 210. This is basically your x1, this is basically your x2. This is basically your y1, this is basically your y2. This is x, this is y. That's how you should relate it. My dear warriors. So basically one value will be basically 10. Other value will be basically 210. Those are the Pandu values for freezing and boiling. Understood? Okay, that's how you will put it on one of the axes. Similarly, for Champa values, you will look at these values over here, minus 20 and 30. So minus 20 and 30. I know I am not drawing it very accurately, but just imagine this. This is minus 20 and let's say this is plus 30. This is plus 30. So that's all. Just imagine one point here. Imagine another point here. Just imagine a straight line passing through these points. Just imagine a straight line passing through these points. And you are interested what will happen at 110. You are interested what will happen at 110. What is the value that you will get? Basically, you are interested in this y value. You are interested in this y value. That's how the problem comes out to be. Isn't it now simpler? Isn't it now simpler, my dear warriors? So what will your answer be? Use this equation. Use this equation. Which one? y2 minus y1, x2 minus x1, y minus y1, x minus x1. So over here, if you notice, this is y2, this is y1. So it will be nothing but 30 minus minus 20 upon x2 minus x1. 210 minus 10 will be equal to y minus y1. That means y minus minus 20 upon x minus x1. 110 minus 10. So 30 minus minus 20 will become 50. 210 minus 10 is 200 is equal to y minus minus becomes plus. This will become 100. This will just become 1 by 4. This will go on the, or 4 goes with 100 25 times. So 25 is equal to y plus 20. 25 is equal to y plus 20. So therefore, y will be nothing but 5. So hence, I got the answer. The y value is 5. That means in that Pandu Champa problem, this will be 5 degree Champa. This will be 5 degree Champa. So that's how you can go from any scale to any scale. Understood? Yes, JEE students can also listen to the class, but don't worry, there are JEE lectures on our separate Vedantu JEE English channel. So now, will you be able to go from any Pandu scale to any Champa scale? You put one on the x-axis, put another one on the y-axis. Put one on the x-axis, another one on the y-axis, and use this formula. Very, very simple looking formula only. There is nothing miraculous about this formula. Very easy looking formula, very easy to solve these questions also. Now let's go to thermal expansion. Let's go to thermal expansion. Everybody ready for thermal expansion? Can you think of some example of thermal expansion? And you might be wondering, sir, what is this thermal expansion? These images should be like a clue to you. What is thermal expansion? Thermal, temperature, expansion, expand. When you heat something, it expands. And you have seen this normally everywhere. You take a, probably metallic scale or metallic object, you heat it, it expands. You might have seen your doors, in summers or winters, they are difficult to open. Depends on whether the door is big or the door is small, or whether, the door is made of wood, plastic, whether the frame is wooden, the frame is metallic, all that decides whether it will give you problems in summers or winters. You might have seen the railway tracks have some gaps in between. And you might have seen certain, windows, etc. They might be difficult to close or open in some hot weather or some cold weather. A jar might be very difficult to open, but you put it in freezer or heat it, suddenly it becomes easier to open. These are very good applications and examples of thermal expansion. So, whenever you heat something, the molecules gain a lot of energy, they require more space, so that's why it expands. When you cool something, the molecules do not move so much, they do not need so much of space, that's why the object contracts. Some objects expand really well and contract really well, they are very sensitive, whereas some objects, they do not respond so much to temperature changes. In fact, that can be useful also. Why? Because imagine you have some nut or some bolt, let's say it becomes hot and the nut becomes very big, so it will become loose, it might just come out. So that's why in certain cases you want that the object should not be so sensitive to temperature and it should not expand so much. So if the nut is made of a very insensitive material to temperature, so even if the temperature increases, it won't change its size, it will still remain tight on that screw. Are you getting me? Everybody with me? Why do you leave this gap? So that in summer, when the railway track expands, there is some space for it to expand. That small gap is enough for it to expand. Else, if there is no space, then it will start bending. That's why even bridges and flyover, have you seen there are gaps in the bridges and flyover? Have you seen there are gaps in the bridges and flyover? Exactly. And do you know where thermal expansion is used in medical science? Can you tell me at least one application of thermal expansion in medical sciences? Because you are going to be doctors. That's why I'm asking you. Yes, no, you're going to be doctors. 100% you will be. Why not? You're attending my class. You will become a doctor, man. Okay. So one such example is, have you seen that some people when they get a fracture or break their hand and they put a plaster, okay, but sometimes the what do you say, the bones are broken to a large extent and they put rods inside. Have you seen that? They put rods inside. Okay. So when they put that rod inside, that should have same thermal properties as the bone. Else, imagine suddenly it is hot, nicely it is expanding. It will come out of your ankle only or elbow. If it expands and cools, suddenly in summer it is coming out, winter it is coming in, it is sucking, it is making a hole only in your skin. So you want to make sure it has the same thermal properties as your bone. Second example is thermometer. Exactly, it is there over here. Thermometer. The mercury inside expands when you put it under your arm because the temperature is hot here. So it expands and it rises up in the bulb. It rises up in the bulb, showing you the temperature. Understood? So many examples are there, my dear students. Okay, so many examples are there for thermal expansion. Okay, so let's have a look at the different expansions that you usually look at. There are three expansions that we look at in any body. One is the linear length, second is the area of that shape or that patch on that object, third is the volumetric or the volume of the object or the volume of a part of that body which is expanding. So we are going to see three parameters inside an expansion. Any body will expand. You can take 2 points and see how much is the length changing. You can paint something and see how much is the area changing. You can also measure the volume and see how much is the volume changing in the same object. These are not different objects. You're just measuring different parameters. Understand that. Okay. So starting off with linear expansion. Look at this. So there is a nice rod. I'm heating it. It will expand. Swing karke it will expand. So let's say L0 is original length. Original length. And L is the final length. Is the final length. And delta L, which is L0 minus L, is the change in the length due to temperature change of delta T. It is found completely experimental. The change of the length is directly proportional to the original length as well as it is proportional to the change in temperature. It's nothing but directly proportional. It's directly proportional to the original length as well as how much is the temperature change. I don't like proportionalities, I want constants. So I will replace it with a constant called as alpha, and this will be L0 and a delta T. You might be wondering, what is this alpha? Well, this alpha is called as the coefficient because length, line, linear. So coefficient of linear, because length, line, linear, that's the reason for that. Coefficient of linear expansion. What does it depend on? Completely depends on the material. Aluminium will have different alpha. Steel will have different alpha. Stone will have different alpha. Pandu's head will have different alpha. Cement will have different alpha. Iron will have different alpha. Understood? It is a material property. If something has more alpha means what? It is sensitive to temperature. If something has alpha close to 0, that means it doesn't expand. It does not react only. So it hardly expands, I would say. It hardly expands or contracts. It hardly expands or contracts. Is that clear, my dear warriors? Everybody with me? Awesome. Now, since delta L is L naught minus L, I can also write this as, L naught, oops, sorry, I wrote L naught minus L, my bad. I should have written L minus L naught because L will be more, L naught will be less, sorry. So this will be L minus L naught will be equal to alpha L naught delta T. Rearranging this further, if I take L naught on this side, what will I get? I will get L is equal to L naught is common, 1 plus alpha delta T. This is also same as this but written in a different form. That's all. It's just written in a different form. So if you want, you can remember this formula or you can also remember this formula. It's one and the same thing. This or this, one and the same thing. This or this, one and the same thing. Is that clear? Very good. So alpha decides how much will it expand or contract when you heat or cool it. Delta T is the change of the temperature. Now, similarly, you have areal expansion. You heat something, take a plate, heat it, its surface area will increase. So that is areal expansion. So same way, just like before, if I tell you original area is A naught, the change in the area is delta A, I can say that this delta A is proportional to the original area as well as the change in temperature. This is original area, and obviously delta T is the change in temperature. That constant of proportionality, this is the change in area, is now beta. So it is beta A naught delta T, and delta A is final minus initial, and you can take this A naught on this side. So A naught will be common, so it will be 1 plus beta delta T. So again, you can see the formulas look very similar here or even here. You can remember this or you can remember this, it's one and the same thing. What is this beta? Beta will be called coefficient of areal expansion, area wise, coefficient of areal expansion. Just like before, it also depends on the material. If it is more sensitive. If it is zero, it hardly will expand. Okay, so that is areal expansion, very similar looking formulas. Yes. Now, last one is volume expansion. You can see this body, you heat it, it is expanding. All the three dimensions are increasing. So same way, just like before, I can say the change in volume is directly proportional to the original volume and the change in the temperature. This is your original volume. This one is your change in the volume. That constant of proportionality I don't like, so I'll replace it with a new constant called gamma V naught delta T. Change in volume is final volume minus original volume into gamma V naught delta T. Taking V naught on this side, I will get V naught common 1 plus gamma delta T. It's like I'm rewriting the same slide again and again, right? 3 times I'm writing the same thing, only instead of length it is area or volume. So you can use this formula or this formula, it's one and the same thing. What is this gamma called? This is called as the coefficient of volume expansion. Let me ask you a simple question. Can gamma be positive? Can gamma be negative? Is it necessary that gamma is only positive? Is it necessary that gamma can be negative also? Think about it. Answer is yes, it can be both positive or negative. This is normal behavior. Most of the bodies behave like this. Example, metals, wood, stone, all All of them behave the same way. What about negative? This is also possible. This is called as anomalous behavior. Anomalous behavior. Example, water between 0 degrees Celsius and 4 degrees Celsius behaves like that. Usually when you heat water, it expands. But between 0 and 4, you know, when you heat water at 0, it does not expand. At 1 degree, it will be smaller. At 2 degree, even smaller. 3, even smaller. 4, even smaller. After 4, again, it begins to expand. That is abnormal behavior. This is normal, abnormal or anomalous behavior of water. Is that clear, my dear warriors? Everybody should realize this. Very good. Is there some relation between alpha, beta, gamma? Yes, why not? Beta is 2 dimensions. Beta is 2 dimensions, area, length, breadth, right? So remember that 2. So it is 2 times of linear. Gamma is length, breadth, height, volumes, 3 dimensions. So 3 times of that linear value. That's all. So this is also very important. If somebody gives me beta, then I can find alpha. If somebody gives me alpha, I can find beta. If somebody gives me alpha, I can find gamma also. Right? As simple as that. Is that clear, my dear students? Shall we proceed? Shall we proceed? What if I tell you? What if I tell you the beta is, example, just taking a random example, 12 into 10 to the power minus 5. 12 into 10 to the power minus 5. What is the value of gamma? Let's see how many of you are able to figure this out. Let's see how many of you are able to figure this out. Beta is given, find the value of gamma. Remember, beta is 2 alpha. Gamma is 3 alpha. So if I divide them, gamma by beta, it will be 3 alpha divided by 2 alpha. Alpha, alpha cancels. It will be 3 by 2. What it means is gamma is 3 by 2 times of beta. Gamma is 3 by 2 times of beta. So 3 by 2 times of beta. What is beta? 12 into 10 to the power minus 5. 12 divided by 2, 6. 6 3s are 18. So 18 into 10 to the power minus 5. That's the value of gamma. Is that right? Everyone? Understood how to find it? How to find it? Very good, Alekhya. Awesome. So you can go from any point to any point using these simple formulas which I have given over here. Let's have a look at some questions. There is some blacksmith. This was, this is already there in exercise 10.2 if you open it in NCERT. Like I said, we saw the NCERT questions also. Blacksmith fixes an iron ring on the rim of a wooden wheel. The diameter of the rim and the iron ring are this and this respectively at 27 degrees Celsius. To what temperature should the ring be heated so as to fit the rim on the wheel? The diameter of the rim and the iron ring are given. Read the question carefully. Read the question very, very carefully. What is given and visualize it. See, the diameter of the rim is given and that is 5.243. The ring is 5.231. This is slightly less. Oh, maybe there is a deliberate reason for that. What could be the reason? If this is the rim, if this is the rim and that rim is given to be slightly larger than the ring, it's because only after heating it, it will fit inside. So the ring actually will be slightly smaller. This is the ring. This is the ring. This is slightly smaller and this diameter is given to be completely different. Completely different. So you need to expand it slightly so that it fits onto it. So when you expand the ring, then it will fit onto it. So how much expansion totally is needed? How much total expansion is needed? This is the expansion needed. This is the expansion needed so that it will fit when it is heated. Yes, everybody, the difference of the two. The difference of the two, everybody, yes or no? Yep. So the delta length formula, if I use L naught alpha delta T, Why am I using the linear formula? Because we are talking about diameter, radius. These are lengths. Lengths means linear. Don't use area or volume. Okay? That's the reason why we are using this. Delta L is L naught alpha delta T. The delta L is how much should it expand? How much it should expand is 5.243 minus 5.231. 5.231. Is that clear, everyone? Is that clear, everybody? And this will be equal to original length. What is the original length? 5.231 into alpha. Is that alpha given? I think in the NCERT book it was given. Just check what is the value in NCERT. Let me also just open it up. Let me also, just 1 second. Let me see if I have that NCERT somewhere. I think it is given to be 1.2 10 to the power minus 5. Just check. The alpha value is given as 1.2 into 10 to the power minus 5. The whole thing into delta t. The whole thing into delta t. Solve this. You will get the value of delta t. But remember, delta t is final temperature minus initial temperature, which is 27 degrees Celsius. 27 degrees Celsius. Solving this, you will get the final temperature. So I think I put up the calculations over here. So I think you get it as 218 degrees Celsius. You get it as 218 degrees Celsius. Is that very clear, my dear warriors? Okay, yes. So in the NCERT problem, if you see the solution also or whatever the thing, so they have assumed that the alpha is 1.2 into 10 to the power minus 5 from the table, that there is a table, okay, of all the alphas of some different elements. You can check that out. I think you can see it is there in one table. What is the alpha for iron? Just check it out. It is table 10.1. It is table 10.1. Yes, the value of alpha. Please use this value from the table 10.1 for iron. It is given. For iron, it is given, okay, because it is clearly mentioned it is an iron ring. Okay, use it from the table. Is that okay? Or else many people get confused, sir, where did that come from? How to do this question and all of that. Okay, okay. Right, let's move on to the next problem coming up on your screen. The coefficient of linear expansion of pendulum is alpha. The change in the temperature is delta theta. Find the fractional change in the time period of the pendulum. Very common question in NEET. Very, very common question in NEET. No, Abhinya, don't memorize the table, because in the NEET exam or even in the board exam, they will give you the value of alpha. How can you by heart? It's so difficult. Don't by heart that table or anything, okay? So only in NCERT, they are lazy fellows. Very lazy fellows. Just to give one value, they could have just written, no? Chumma, confusing students. The student will be like, what nonsense, I have to by heart. Unnecessary confusion, not needed. Okay. So, my dear warriors, over here, when you change the temperature, when you increase the temperature, the length of the pendulum will increase. And as soon as the length of the pendulum increases, the time period will also change. So, changing the temperature changes the time indirectly. So, first of all, you should know what is the time period of a simple pendulum. Standard formula is 2 pi root of L by G. That's the formula. Standard. Okay, if you don't remember it, it's okay. Now, I'm telling you that is the formula. Just take it for granted. Okay. Now, next thing what you will do is write it in the power form, because actually it's a question on units, dimensions and errors also. Why? Because when you change length, time period also changes. So why not write it like this? 2 pi root of G, the power of L is half and this is time. These are all constants. So when I write the relative error of time period, relative error, change upon original, constants don't matter. You write relative error of length upon that original value, and whatever is the power comes over here. This is from the chapter of errors. This is from the chapter of errors. Wow, whatever the power is there, it comes outside and that fractional error comes over here. Okay, now do I know the value of delta L? Of course. Delta L is nothing but original length alpha into change in temperature. Here the symbol used is delta theta. Don't get confused. Sir, change in temperature should be delta T, no? Yes, it can be delta T, but if you put delta T, students will get confused and cancel this. But remember, you cannot do that because this is temperature, this is time. So don't do that. That's the reason why, to avoid the confusion, we use a different symbol only. No confusion. That's it. LL cancels. So delta T by T will be alpha delta theta by 2. What is asked? Find the fractional change in the time period. Exactly. The fractional change in the time period is exactly this. So it is alpha delta theta by 2. Alpha delta theta by 2. Is that clear, my dear warriors? This only is that fractional change in time period. This is exactly what we wanted. Cool. If alpha is given, temperature change is given, you can find how much does the time period change relatively. That's one thing. Now look at this question. This was asked in NEET 2019. What does it say? A copper rod is given, aluminum rod of unknown length is given. They have equal lengths and their lengths are independent of the increase of the temperature. Question is, find the length of the aluminum rod. Question is, find the length of the aluminum rod. Let me make you visualize this. See, you have, for example, that copper rod is there, okay, and you also have the aluminum rod. They have of an unknown length. Okay, this is of an unknown length, not even given to me. Now when you increase the temperature, what happens? They both have an equal increase in the lengths independent of the temperature, meaning if temperature is raised, this increases some amount. Even this also increases by the same amount. So whatever delta L is here for aluminum, I call it delta L2, and delta L for copper, I call it delta L1. These both are given to be equal. So delta L1 is equal to delta L2. So always draw diagrams. Then see what is given in the question. Some condition will be there. Write that condition. That's how you solve physics problems. Always, wherever possible, even in temperatures and thermodynamics, wherever possible, draw, visualize what is given, what is not given. Then you will understand, oh, the changes in the temperature are same. What is delta L1? Delta L1 is original length, alpha and delta T, correct? And what is delta L2? That is original length, alpha 2 and delta T. Can you not see, my dear students, this delta T and this delta T cancels because it is given for the same increase in the temperature. Now what is L1 value? The length of the copper rod is 88. Alpha of the copper is 1.7 10 to the power minus 5 is equal to length 2. That only I don't know. Alpha 2 is 2.2 into 10 to the power minus 5. Solve this, you will get the value of length 2. Krishna and Shiny saying option A. Even Alekya saying option A. Whether you guys are right? Wow, yaar, you guys are amazing. 68. Yes, that is the correct answer. Solve this. Just take this over here. 10 to the power minus 5, 10 to the power minus 5 also cancels, and you will see that the answer comes out close to 68 centimeters. Is that clear? In fact, it is very simple. 22 goes with 88 4 times. 17 4za. That's it. 17 4za 68. Cool. Shall we go ahead to the next one? Yes, A for Ames was the answer. Moving on. Next question. Look at this. These kind of questions are also very common. Density changes. A liquid has some density, some volume. Coefficient. Wow. Temperature changes by 10 units. The new density is, if this question comes, no, I'm telling you, many people will either do it wrong or will not know only how to do. But because you are here, you will get full marks. Common kind of question which can be asked. Density related. Now, when you expand something, the same mass has more volume. Because it has more volume, the density goes down. Okay, cool. So, if I write my original density to be mass by original volume, then my new density will be that same mass by a new volume. Can I write something instead of that volume? Because I don't know only that volume. I think so. That volume, I can use this equation. Where is that? I'll just show it to you. See, right over here. Final volume is original volume 1 plus gamma delta T. Remember, we just did it during volume expansion. So why not use this equation over there? And see what happens exactly. So this will become original volume 1 plus gamma delta T. Oh, but wait a minute, m by V naught, that is nothing but the original density. Is that right, everyone? M by V naught is rho naught, and this 1 plus gamma delta T will stay here. Perfect. Original density, I know. Gamma, I know. Delta T, I know. Wow, very good. So, rho, the new density, is rho naught. Rho naught is 1000 divided by 1 plus gamma. 1, 2, 3, 4 decimals. So, 10 to the power minus 4 into 10 units. That's the delta T value. So, this will become 1000 divided by 1 plus 10 to the power minus 3. Now you know what many legendary, ultra legendary people will think. Sir, 10 to the power minus 3, sir. Oh, sorry, there were how many? 1, 2, 3, 4. Sorry, this was 10 to the power minus 5. My bad. One second. This was 10 to the power minus 5 into 10. So this will become 1000 divided by 1 plus 10 to the power minus 4. So many ultra legendary people will think, sir, this value is very small compared to 1, ignore it. No. Very good. Ignore it. So this will become 1000 divided by 1. 1000 divided by 1. Like 1000 divided by 1000 only. Sir, it is 1000. Answer is 1000. One tight slap I should give. Then why will the examiner waste his time and effort and energy and money to make this question? Increasing the temperature, no change only in density. Think logically. Answer will be slightly less than 1000. Understood? Got it, everyone? So don't be that legendary person or ultra legendary person who thinks very smart. 1000 is the answer. One tight slap only. So what you need to do, you should understand this is 1 plus small number form. 1 plus small number form, which is binomial approximation form. So bring that on the top. It will become 1 plus 10 to the power minus 4 raised to minus 1. Oh, now it's looking like binomial raised to n, and you can use that approximation formula, which is now going to be 1000. What is that formula in case you have forgotten? What is that formula? 1 plus small number raised to n is approximately 1 plus nx. 1 plus nx. This is the approximation. If you don't know, don't remember, okay, I am telling you this. Just remember it now. Oh, perfect. So what will happen? This will be approximately 1 plus n. N is minus 1. X is 10 to the power minus 4. 10 to the power minus 4. So this will be 1000 1 minus 4 10 to the power minus 4. So I'll have to put 3 zeros over here. 3 zeros over here. And then 1. So what will this be? 1000 and 1 minus 0.0001. What will it be? 0.999. 999. Multiplied by 1000, you will get it 999.9. This is the answer. So it's slightly less than 1000 and the answer is 999.9 in this scenario because everything was like in tens. If the values were different, then obviously it might be 998, 996, 997, but some nice values were there, so we got a nice number also. Did you love the number? I love this number, yeah, 999. Very nice number. है ना? And especially when you are riding scooter or you are driving a car, and when that 9999 comes, you know, it's very interesting to see, especially the old cars and the old bikes, not the electric ones, okay, the old one. So once it becomes 999, then everything becomes 0 and then you get 1 or 2 or 3 or something like that. Have you seen that somewhere? Have you seen that somewhere? Maybe in the old bikes or old cars. Okay. Digital mein you will not see. Apparent expansion. What is this apparent expansion? You know, there was a student, very legendary student. So you know what legendary students do. He was heating. I've seen that student, you know, amazing. Ultra legendary student he was. He was heating water in the test tube, in this beaker. Some liquid, not water, some liquid. And then after heating, he saw that the level of water went down. Just like Archimedes ran out of the tub naked, saying, "Eureka, Eureka, I discovered something." This student also ran, luckily not naked. Okay? He ran like one fool and it's like, "Sir, sir, oh my God, come everyone, come everyone. I found one magical liquid. After heating, it does not expand, it falls down, the level goes down." I was like, "Come here. Come here. What are you saying? I'll teach you, sit over here, I'll teach you apparent expansion. See, you heated. You thought the water or that liquid, whatever was there, should expand. But instead, you saw the level went down. And then you thought, oh, that liquid is contracting. Hero, listen. Did you forget? Even that beaker, that container, that tube was also expanding. Oh. Now we are going somewhere. Maybe that beaker only expanded more than that liquid inside. So if it expanded more, then the liquid also tried to expand. But because the container, the beaker, the test tube, whatever it was, expanded more, maybe that level would have gone down. Did you understand this phenomena? Did you understand this phenomena, everyone? Very good. This is what is called as apparent. Means what you feel, what you probably end up seeing. It is not actual. It's apparent, like apparent depth of the pool is a little bit different than the actual one. Got it? So, same way, when you heat a liquid or anything inside a container, you need to accommodate for the container's expansion also. So, it so happens that if the volume of the container is Vc, the gamma of the container is gamma c, and the temperature change is delta T, the change in the container's volume is given by this formula. Similarly, if the liquid inside has a volume till where the container is filled, I am considering Vc as that volume till which the liquid has been filled. The volume till which the container has been measured or the volume till which the liquid has been filled is called as Vc. So that is the volume of the liquid. Gamma of the liquid is gamma L. Change of temperature is delta T. Then you will see the change in the liquid. The change in the liquid volume will be delta VL given by this formula. Now, when you subtract the two, right, this minus this, this minus this, then you get what is called as the apparent change in the volume. This is delta V apparent, which will be Vc is common. This will be gamma of that liquid minus gamma of the container into delta T, which you can also write it as gamma apparent delta T. This is your delta V apparent. You are subtracting this with this. So gamma apparent is gamma of the liquid minus gamma of the container. This is gamma of the liquid. I think it is not seen so clearly. I'll just write it again. Gamma of the liquid minus gamma of the container. So what you measure is this. If you know the container's gamma, you can also find the gamma of the liquid. You can also find the gamma of the liquid. Is that clear, my dear warriors? Everyone? Okay, so this is apparent expansion formula. But more than the formula, the questions can be really tricky. And one such tricky question I have for you. If you can solve all the 3 questions, you are a real genius. AIMS is waiting for you. AIMS is waiting for you. AIMS Delhi or any AIMS is waiting for you if you can get these questions in one go. So listen to the question. Excuse me. An object's length is 20 centimeters at room temperature. Find the reading shown if it is more, if it is less or equal to 20 centimeter in each case when heated. First case, there is a wooden object. The scale which is used is steel. Second case, the object is made of steel and the scale is made of wood. And in the third case, it's a steel object and a steel scale. Wow, 3 different scenarios. Let's take everything one by one. Let's take everything one by one. Let me create a duplicate. Okay, imagine the first case, which is wooden object, steel scale. Wooden object, steel scale. So this is an object which is made of wood and there is a steel scale over here. There is a steel scale over here, something like this. This is made of steel. This is made of wood. Now when you heat it, who expands more? Obviously steel. Wood does not expand so much. In fact, the expansion properties are much lesser for wood as compared to steel, steel being a metal. So earlier it used to show the reading of 20 over here. 20 centimeters was shown here at room temperature. So when both are heated, what will happen? Maybe the wood will expand, maybe not so much, maybe this much. But what will happen to steel? The steel scale will expand a lot. Relatively, I know this is highly exaggerated, but can you visualize? So will the 20 mark also move only till this point? No, right? It will expand more. That means maybe the 20 mark will come over here. Maybe that 20 mark which was there, maybe that 20 mark which was earlier here, now that 20 mark will come over here. So at this new temperature, will you see the value on the scale as 20, more than 20 or less than 20? Answer in the chat box. Answer in the chat box. Come on, think about it. Think about it. When you heat it, you will see the value that you get over here will be 100% less than 20 centimeters. You will feel that the wood has contracted. You will feel that the wood has contracted. Alekia said less. Very good. Very good. So you will measure less than 20 centimeter. Is this first situation very clear? Very good, Dipanvita Chatterjee. Yes. Shazin, yes, it is going to decrease. Now let's take the second case, steel object, wooden scale. Steel object, wooden scale. Steel object. This is made of steel. And we have wooden scale. We have wooden scale. The wooden scale shows 20 over here. When you heat it, the wood might hardly expand anything. This 20 might just reach over here. This 20 might just reach over here. But the steel, that will expand a lot. That will expand a lot. Can you see that? 100% it will expand by a lot of amount. And the reading that will be shown over here, 100%, it will be beyond 20 centimeters. Beyond 20 centimeters. Exactly. Now, what about the last one? When both are made of steel, when the scale is also made of steel and the object is also made of steel, both are made of steel, then both of them will expand by the same amount. Meaning earlier, wherever you saw 20, that 20 will now reach over here, will now reach exactly over here. Okay, this will be exactly 20 centimeters because both of them will expand together. So you will feel, oh my god, the object didn't expand only. But little do you realize that, oh, wait a minute, even my scale has expanded. So maybe that's why I did not get the true reading. So this is the concept of apparent expansion. Here we saw no apparent expansion. Here we saw more than what you got. And here we saw less than the original value. So beautiful question, conceptual question can come in NEET. Next, thermal stress. Everybody has exam stress. Everybody has exam stress. Everybody has lot of stress, sir. Too much homework stress, sir. Practical stress, board stress. What is this thermal stress and thermal strain? Very simple, I'll tell you. If you take an object and allow it to heat freely, this is at temperature T. If you allow it to heat freely, then you will see it will try to expand. This is maybe at T plus delta T. But then imagine you are like, no. I won't allow it to expand freely. I want to bring it back to its original shape and size. I won't want it to expand freely. I want to make sure it comes back to its original shape and size, meaning I am holding it from both sides with rigid supports. It is wanting to expand. So it wants to expand. It wants to expand. But you can see clearly it is compressed. Because it is compressed, there must be a force which will be compressing it. There must be a force which is compressing it from both sides. And that force per unit area will be the thermal stress which is developed. So the thermal stress, usually the symbol is sigma TH, is the force divided by area. This force is compressive in nature because it compresses, it is not tensile. Okay, it is trying to compress it. Okay, how much is it? We can easily find it out. It is not that difficult. How to do it is, remember Young's modulus is stress by strain. Therefore, sigma is Young's modulus into strain. Strain is change in length upon original length. This is the thermal strain. But wait a minute. I know the value of delta L. It is original length alpha into delta T. So LL will get cancelled and we will be left with Y alpha delta T. So that's the value of the thermal stress. That's the value of the thermal stress which is developed. Y alpha delta T. Young's modulus into coefficient of linear expansion into the temperature change. As simple as that. So let's have a look at a question coming up on your screen. A rod is drying freely on a horizontal surface. Find the thermal stress and the thermal strain produced in the rod if it is heated by some temperature. If you answer this question, I will be really proud of you. I'll be really proud of you. Very easy peasy question. Come on. Very easy peasy question. Lemon squeezy. Biryani easy. What is the answer? Read the question carefully. It is lying freely. Here, it was not free. It was attached between the rigid supports. If it is free, it will nicely expand. Why will there be any stress? No stress, no strain. Answer is a big fat 0. Answer is a big fat 0. Some of you got it. Some of you got it. Got it, everyone? There is no reason only. Arams and nicely only it will expand. Very good. But in this question, rod of certain length is at certain temperature. Find the free expansion of the rod if the temperature is increased to 50. Find the thermal stress produced when the rod is fully permitted to expand by 0.4 meters and all of this. Okay. So, in these kind of questions, what will you do? In these kind of questions, what will you do? Come on. Everyone, first of all, find the free expansion of the rod. Just let's try to find what is the free expansion of the rod using this formula delta L is equal to L alpha delta T. What is L? Original length, that is 2. What is alpha? Alpha is 15 into 10 to the power minus 6. What is temperature change? 20 to 50. So it is basically 50 minus 20. 15 2s are 30. So 3 into 10 to the power minus 5 into 50 minus 20 is again 30. So 3 3s are 9. So into 10 to the power minus 4. So how much is it? Basically 0.9 millimeters. This is meters. This was 0.9 millimeters. Everyone with me on this? Everybody with me on this? Clearo, pakka, done, done. Now, for the first part, when it is fully prevented to expand, then the thermal stress in the first case will be given by Y alpha delta T. Y alpha delta T. What is the Young's modulus? 2 into 10 to the power 11. 2 into 10 to the power 11. Alpha is nothing but 15 into 10 to the power minus 6 into delta T, which is nothing but 30. So 2 into 15, 30. 30 into 30, 900. So you will see it will be 9 into 10 to the power something. Yes, 9 into 10 to the power 7. Yep. So this will be 9 into 10 to the power 7. This is always force per unit area. So Newton per meter square. That is the first case. 9 into 10 to the power 7. Very nice. Now the second part, where it is permitted to expand but only 0.4 meters. Actually it wants to expand how much? 0.9. But how much did you permit? 0.4. So how much strain was developed? How much did you actually allow it to expand by 0.4? So basically, how much was the delta L value over here? Won't it be 0.9 minus 0.4? It wants to expand till 0.9 millimeters, but you allowed only 0.4. So from 0.9, you have compressed it by how much? 0.5 millimeters. 0.5 millimeters. So remember, the stress will be Young's modulus into strain, which is Young's modulus into change in length upon original length. So that's it. Young's modulus is 2 into 10 to the power 11. Delta L is 0.5 of a millimeter. That means into 10 to the power minus 3 upon original length, which is basically 2. Is that clear? So now solving this, 2 gets cancelled and you will get this as 5 into 10 to the power, check this out, 10 to the power minus 4, 10 to the power 11, that will make it 10 to the power 7. 5 into 10 to the power 7, that should be the answer. Yes, 5 into 10 to the power 7, that's the second answer. Obviously this will be Newton per meter square. That's the second answer. Is that clear? These are all NCERT based questions. Amazing. Now let's go to the second part and the final part, which is heat calorimetry, specific heat capacity. Very straightforward questions are there. Now in the second part, after studying how much does the object expand or contract, okay, after being heated, the second part is all about when that heat is given to it, then the temperature changes, and you will see that for the same heat every object will change the temperature by different amount because they have different heat absorbing capacities. Same teacher is teaching everyone. Some students understand it really well, some students understand it decently well. Some students score really well, some students score average because the heat capacities are different. So how do you actually solve the problem for NEET? That's why you do many revisions. So even if you are a slow learner, it's okay, but you learn it many times so that delta, delta, delta integrates and it becomes a big value. And then you understand or solve problems at the exact same way as that of another person who can understand it in the first go. So there is always hard work which pays off. So my dear warriors, heat, we all know, is nothing but the transfer of energy from one body to the other body. Heat flows, right, from hot side to the cold side. We know heat is a scalar quantity, heat is measured in joules, right? So we know all these things. So what does this heat do? This heat can change the temperature. This heat can change the temperature. Okay, so I have a body of a certain mass and I heat it. I give it Q amount of heat to it. Because of that, the temperature of the body changes by delta T. You will see that the heat supplied, to a body is directly proportional to the mass of the body and also the change of the temperature. I don't like this proportionality. I want a constant. So I'll put up a constant, no worries. So the heat supplied is Q is equal to mass is M, change in temperature is delta T, the constant is S. This S is nothing but specific heat capacity. Specific heat capacity, as simple as that. Q is equal to ms delta T, S is the constant of proportionality. This specific heat capacity completely depends on the material. Example, for water, the specific heat capacity is 1 calorie per gram degree centigrade. So if you take 1 gram of water and you increase the temperature by 1 Celsius, you will need 1 calorie of heat. So usually the units of S are either joule per kg Kelvin, or sometimes you also use calorie per gram degree centigrade. All right, both of them are units of specific heat capacity. It completely depends on the material, whether it's water, ice, or alcohol, or some benzene, or maybe some other solid, maybe stone, marble. Everything has different specific heat capacity. Keep that in mind. Very nice. Then apart from, so usually this is used for solids. Apart from this, you might have gases, and gases are usually measured in moles. That's when you do not write mass. Mass is generally for solids, liquids, it's okay. For gases, you use moles. So if you have a gas, and the number of moles is N, and you heat the gas, by giving it Q amount of heat, and you see that the temperature changes by delta T, then I will say that the Q value is, instead of M, it will be N, number of moles, and delta T will be there. And here I will use the symbol C. This C that you see over here, is molar specific heat capacity. This is just specific heat capacity. Here the units will be joule per, just like this was per kg or per gram. Here it will be per mole per Kelvin, or you can also use calories per mole per degree centigrade also. That is C value. That is your C value, which is molar specific heat capacity. And it also depends on how you are heating it. We have already seen for constant pressure, at constant pressure, we have seen Cp is used, and at constant volume, if you heat it, then you will use Cv. And remember, Cp minus Cv Remember this? Cp minus Cv was R, which was your Mayer's relation. Mayer's relation. Mayer's relation. We have also seen this value, Cp by Cv, is nothing but gamma, which is 1 plus 2 by F degrees of freedom. Gamma is the ratio of Cp by Cv. All these formulas we have seen in KTG and thermodynamics. So I'll not focus on it again, but this is just like a recap of that. Okay. So for solids and liquids, this is what you use: specific heat capacity, which is measured per kg per Kelvin. For gases, you use it per mole per degree Kelvin or per degree centigrade. Thank you so much. Glad you are enjoying the lectures, Arun. And I'm so glad when I see these comments. So quickly answer this question. The ratio of Cp by Cv is gamma in terms of degrees of freedom, and it is given by, come on, gamma is given by 1 plus 2 by F. That's what I just told you over here, 1 plus 2 by F. So here the value of F only is N. So 1 plus 2 by N, where is it? B for biology. Very nice. Good. Next question. The amount of heat energy, this was asked in AIPMT 2013, to raise the temperature of 1 gram helium from this to this is how much? 1 gram helium is how many moles? Moles 1 by 4, because molecular weight of helium 4 grams per mole. So it is 1 by 4, that is N. And amount of heat energy required to raise the temperature at NTP. My dear students, which formula will you use? Which formula will you use? NC delta T. NC delta T. So Q is basically NC delta T, assuming that this is done at constant volume. Okay, there is no change in the volume. Let's assume that. So then number of moles is 1 by 4. What is the value of Cv? Because this is helium, it is monoatomic. So Cv value will be 3R by 2. For monoatomic, it is 3R by 2 and into delta T. So this will become 3 by 8. Instead of R, can I write it in terms of Boltzmann constant? Remember, Boltzmann constant was R by Na. So if I take Na over here, R will be replaced with K times of Na, and delta T is nothing but T2 minus T1. So I think such a option is there over here. K into Na 3 by 2, and this is your T2 minus T1. So that is option A. This was a simple AIPMT 2013 question. Yes, very nice. Awesomeness. Cool. Now you also have something called as the water equivalent. Water equivalent, meaning if you have a body of certain mass, and you are providing some amount of heat, and you see that the temperature changes by delta T, then if you provide that same heat to some water, okay, to some water, that mass of the water which is needed so that the temperature changes by the same amount is called as the water equivalent. Why do I convert it into water? Because water has a special value of specific heat capacity, 1 calories per gram per degree centigrade in calories unit. So, and most of the things around us are measured in terms of water, relative density, specific gravity, all these are measured with respect to water. So, because water is universally very easily available. So, when there is an object, if I convert it into grams of water or kgs of water or whatever amount of water, then I know it will absorb the same amount of heat for the same temperature change. So whatever this water does, that object will also do the same thing. So I can then say for the object, this is for that object, Q is equal to mass of the object into specific heat capacity of that object into delta T. Whereas for the water, same heat, mass of water, specific heat capacity of water into delta T. So because both of them are equal, I can then equate these two. Remember, these are equal. I just told you, heats are same. So whatever is over here and whatever is over here, they are basically going to be equal in amounts. Therefore, the mass of the water will be mass of the object specific heat capacity divided by specific heat capacity of water. Divided by specific heat capacity of water. Keep this in mind. A very simple looking formula, not that difficult. Even if you don't remember the formula, if you remember the phenomena or how it has been defined, you can easily get it. It's not that difficult. Now, whenever you do these problems, one conversion factor might be needed for all of you. So I'm giving you that conversion factor. Remember, 1 calorie is 4.18, which is approximately 4.2 joules. This conversion you might need many times, and more specifically, say for example, specific heat capacity of water is 1 calorie per gram degree centigrade. If I want to convert it into SI unit, first of all, 1 calorie is 4.18 joules per gram per degree centigrade. First I converted calories into joules. Then I will write 1 gram is nothing but 10 to the power minus 3 kg, and this is degree centigrade. This will then become 4.18. When it comes on the top, it will become 10 to the power 3 joules per kg per degree centigrade. Next, this will become 4.18, you can put it as 4180 joules per kg. 1 degree centigrade change is also 1 Kelvin change, right? 1 degree centigrade change is also 1 Kelvin change. We know that. Everybody agrees? 273 to 274 is same as 0 to 1. No change at all. So I can also write it as Kelvin. So 1 calorie per gram degree centigrade is 4180 joules per kg Kelvin. That's how you convert the specific heat capacity of water. Is that okay? Everyone with me on this? Everybody with me on this? So say for example, there was a question saying specific heat capacity of a metal is 0.5 calories per gram degree centigrade. Mass of that metal is 40 grams. Find the water equivalent. In grams only. No issues. Calories, grams is okay. What will we do? Use the formula. Mass of the water equivalent is mass of the object specific heat capacity upon specific heat capacity of water. Mass of the object 40 into specific heat capacity 0.5. In SI units, this is 1 only. So 40 into half, that's going to be 20. So that is 20 grams. So 20 grams of that metal, 20 grams of water, 20 grams of water is like 40 grams of that metal. 40 grams of that metal. That is the meaning of water equivalent. That is the meaning of water equivalent. Is that clear? Give me a thumbs up. Smash the like button. Let me see the likes going up. Even if you are watching it recorded, I will feel very happy when you do it as you watch the recorded class. Cool. Shall we go ahead? So we have reached till water equivalent. We have seen specific heat capacity, molar specific heat capacity, and all these things. Now, what happens when you transform the phase only? When you change the phase only? Well, if water remains water, ice remains ice, steam remains steam, vapor remains vapor, liquid remains liquid, solid remains solid, then the heat supplied is just going to change the temperature. But if you reach the freezing point while doing so, or if you reach the melting point while doing so, or if you reach the boiling point while doing so. Then what happens? Then it changes the state, and then the heat supplied does not go in changing the temperature. I mean, you would have seen this. Imagine you take ice, you heat it. It reaches melting point, which is 0 degrees Celsius. You will see the ice melts into water, and till entire ice melts, the temperature of ice remains 0 degrees Celsius. Have you seen that? Yep. Then you melt it. You will see the temperature remains at 0 degrees Celsius. Very good. Now, once the ice is melted into water, then you heat, then you will see that the temperature again starts rising. So till it is melted, its temperature remains same. After that, the temperature again begins to rise. This is the temperature, this is the heat. Until it reaches 100 degrees Celsius, boiling point. And then the temperature does not change until it converts completely into vapor, and then 100 degrees Celsius steam will become 101, 102, 120, 150 degrees Celsius steam also. Is that clear, my dear students, my dear warriors? Great. So this is a very important graph which tells you how the temperature changes with heat. Mainly what you should note is that any melting, freezing, vaporization, condensation, basically this is called as transformation process. Transformation process. They are transformation processes, whether it is melting, freezing or vaporization, condensation. These transformation processes, they are always at constant temperature. Very, very important. Very, very important. Solid to liquid is called melting. Liquid to solid is called freezing. Liquid to gas is called vaporization. Gas condenses to form liquid. This is a very beautiful diagram to explain that. Ice is at -10. You heat it, comes to ice at 0. You keep heating it, ice remains at 0 till all the ice melts, becomes water at 0 degrees Celsius. You heat the water, from 0 it will go to 20, 30, 40, 50, 90, 100. Then that 100 degrees Celsius water remains at 100 till all the water evaporates, vaporizes into steam. Then the steam becomes 100, and then you can further increase it even beyond 100 degrees Celsius. A beautiful, beautiful diagram, isn't it, my dear students? Awesome. So, is this heat required to melt it or condense it or vaporize it or freeze it related to something? Yes. The heat of transformation is mass into latent heat. This L depends on the process. M is nothing but the mass. This is called as the latent heat of transformation. Say for example, latent heat for ice to go into water, which is the same as ice to go into water means basically for melting of ice is same as latent heat for freezing of water. So water freezes into ice or ice melts into water, it is the same. It is 80 calories per gram. To melt 1 gram of water, you will need 80 calories of heat. 1 gram into 80 will make it 80. So 80 calories are needed to melt 1 gram of ice. If you take away heat of 80 calories from 1 gram of water at 0 Celsius, it will convert into ice. Same way, latent heat to vaporize water is the same as latent heat to condense steam, and that value is 540 calories per gram. You should know this value, huh? You should know this value. It's very, very important. You should know this value. This value also, this value also. This formula you should know. You should know. Is that clear, everyone? Yep. Sublimation is basically directly going from solid to gaseous state without going into liquid, like naphthalene balls. What are naphthalene balls used for? For keeping away insects, lizards, and so many other things. So naphthalene, yeah, it's a very good example of sublimation. So you can see this same diagram. I have put it up over here again. Very, very important diagram. I'm reiterating this fact. This diagram has been asked. How does the diagram of heat versus temperature look like for all the three phases? Standard thing. Okay. So please keep this in mind. Great. So let's go to some questions coming up on your screen. This is NEET 2016 question. Can you solve this? A piece of ice falls from a height h so that it melts completely. Only 1/4 of the heat produced is absorbed by the ice, and all the energy of the ice gets converted into heat during this fall. Okay, the value of h is. So let's understand what is happening. There is ice over here. There is ice over here. Okay, it starts from rest. It falls, falls, falls. All the energy that it has lost gets converted into kinetic energy, and that kinetic energy finally gets converted into heat. So what is happening is that potential energy gets converted into kinetic energy, and that kinetic energy gets converted into heat. But out of all that heat, only 1/4 is absorbed. 1/4 is actually absorbed heat. Absorbed heat. To what? To melt it. Absorbed heat to melt it. Okay, absorbed heat to melt it. Interesting. So think about it. If potential energy is kinetic energy is heat. Kinetic energy is heat. So can I not say mgh is that heat, and dividing it by 4 is the absorbed heat, to melt it. So to melt, what will you do? The heat, you will equate it to m into L. So mgh by 4 is ml. M cancels. So what will I get? H is equal to 4 times of latent heat divided by G value. So 4 times of latent heat of ice is 3.4 into 10 to the power 5. Everything is in SI units, and divided by G, which is 10. Solve this, you will get the answer. 4 3s are 12, so close to 13 point something. Yes, 136 kilometers, or 13.6 into 10 to the power 3 meters is what you should get. 4 3s are 12, you can see that. So it's close to 130, sorry, not 13.6, 136. Yeah, so this will be 136 kilometers. That's what you should get. Is that okay? Is that okay? Weekly mock test, so I have attend them later. Will I get a result? No, you will probably get the marks, but not the rank. So rank obviously is only based on the live testing, not on the other things. Cool? Very nice. So let's go to the next question coming up on your screen. Get ready for it. And here comes the next question. Calculate the heat required to convert 3 kg of ice at -12 in a calorimeter to steam at 100. Okay, specific heat capacity is given, specific heat capacity of water is given, latent heat of fusion is given, latent heat of steam is also given. Very nice question. So let's understand what is happening. 3 kg ice is there. 3 kg ice is there. At what temperature? -12 degrees Celsius. So first, what I will do? I will take that 3 kg of ice to 0 degrees Celsius. 3 kg of ice to 0 degrees Celsius, because I cannot directly convert it into steam. First I will heat it, -12 will become 0. Then what will happen? It will become 3 kg of water. It will melt and become water at 0 degrees Celsius. Then you heat that water. That same 3 kg of water slowly increases the temperature to 100 degrees Celsius. You heat it further. That 3 kg of water will now convert into steam at 100 degrees centigrade. This is an NCERT question. So every process heat is required. What and all the heats are required? Just think about it. Going from here to here, the formula that you will be using the formula that you will be using is ms delta T. Formula for here will be ml. For here, it will be ms delta T. Why? Because the phase is the same, only temperature is changing. Here I am going from water to steam, so I'll use ml. That's all. Now just have to substitute the values. Mass 3. S for ice. Specific heat capacity for ice 2100. 2100. Delta T 12. Delta T 12. ml. M is 3. Latent heat for fusion of ice 3.35 into 10 to the power 5. Then water goes into water from 0 to 100. Mass 3. S specific heat capacity of water 4186. 4186 into delta T. 100 minus 0 is just 100. Lastly, ml. Mass is 3. Latent heat of vaporization or steam, that is 2.256 into 10 to the power 6. These are the individual heats. You just add this, this and this. You will get the total heat. You will get the total heat. Is that clear? Is that clear, my dear warriors? Is that clear, my dear warriors? Pakka? So when you add all of this, I have put the answer on the next slide, I hope. Somewhere. Yes. Let me show it to you. Yes. It comes out huge value. See, all these values. 9.1 into 10 to the power 6. That's the final answer in joules. That's the final answer in joules. Okay. Did you now understand how to go from one phase to the other, or this phase to this phase, etc.? Shall we now go to the next part? You know what is the next part? Okay. We have done this. And what is happening? Suddenly this slide came. Okay. Calorimetry. This is the last part. Let me explain this to you. It's very straightforward. So in calorimetry, what happens is you have a calorimeter or you have an isolated system. So this is a calorimeter. It has a lid over it. Nothing can go out or come in. So this is an isolated system. Isolated system. There might be some really hot objects. There might be some really hot objects. There might be some really cold objects. You leave it inside the system. You leave it inside the system. Isolated system. The heat can't completely go out. Nothing can come in. Mass can't go out. Mass can't come in. Eventually, equilibrium is achieved. So, if hot and cold, all right, objects are left inside an isolated system, which is often called as a calorimeter, often called as a calorimeter, the total energy is conserved. The total energy is conserved, and because of this you get a principle of calorimeter, which is heat gained by cold body. Whatever heat will be given by the or gained by the cold body will be exactly the heat lost by hot body. Very, very important. This is the principle of calorimeter. This is called as principle of calorimeter or calorimetry. As simple as that. Very, very straightforward. It makes sense. Pandu is very cold. Champa is very hot. Pandu makes a sad face. Pandu makes a very, very sad face. Pandu is like, I am feeling very, very cold. Champa is like, don't worry. This is very, very hot, Champa. This is very, very hot, Champa. So, Pandu and Champa, Champa gives a nice warm hug to Pandu. Champa and Pandu, they hug each other very nicely. Look at this, beautiful. Look at this, they give hug. After that, they will exchange heat. Champa loses heat, Pandu gains heat, and finally they will attain thermal equilibrium. Correct? They will attain thermal equilibrium. This is thermal equilibrium. Is that clear, everyone? Straightforward. Yes. This is a love story, beautiful love story. So let's solve some questions based out of this. Okay, so we won't get questions on Pandu Champa, but Pandu Champa always helps us understand very boring or even difficult concepts in a very simple and easy manner. You can never forget this love story, after this, and you can never forget the principle of calorimetry. Total energy is conserved, right? Okay, what is this? Two liquids are at 20 and 40 when same mass of both of them is mixed. The temperature of the mixture is 32. What is the ratio of their specific heat? What is the ratio of their specific heat? That's the question. Come on, my dear warriors, think about it. How are you going to solve this? How are you going to solve this? What are you going to do? Two liquids are at 20 and 40. When the same mass of both of them is mixed, the temperature of the mixture is 32. Here you need to identify who is cold and who is hot. Here the cold one is 20, the hot one is 40. The equilibrium temperature is 32. So what will be the heat gained by the cold body? The heat gained by the cold body, because that will be exactly equal to the heat which is lost by the hot body. The heat gained by the cold body will be mass into specific heat capacity into delta T. So it was at 20, went till 32, so it will be 32 minus 20. 32 minus 20, that's the change in temperature. For the hot body, Q is again ms delta T, mass is same, S is S2, delta T, it was at 40, went till 32, so the change is 40 minus 32, don't put 32 minus 40 or else you'll get negative marks and negative answer also. Cancels. So what will I get when the time thermal equilibrium achieves? So 32 minus 20 is 12 and this is S2 into, how much is it? Again 8 over here. So S1 by S2 will be 8 by 12. Divided by 4, this will be 2 by 3. So 2 by 3 is option D. Yes, that's the correct answer. 2 by 3, that is option D. Very good. What was that? Krishna, very nice, very nice. Very good, very good. Awesomeness, awesomeness. Moving on to the next question coming up on your screen. Two identical bodies of a material, heat capacity only changes with temperature. This was asked in NEET 2016. One of this is at 100, other one is at 0. If the two bodies are brought into contact, then assuming no heat loss then from the surroundings, then final common temperature is exactly 50, less than 50, more than 50 or 0, that's the question. Okay, see, let's say the first body which is at 0 degree Celsius, okay, 0 degree Celsius, that is the colder one, and the hotter one is at 100 degree Celsius. So heat which is basically lost by the hotter one will be given by M S hot into delta T, and similarly for the colder one will gain heat, mass is same into S of the colder one into delta T. Okay, now I don't think these delta T's will be also equal. I don't think these delta T's will also be equal. In fact, if you do the simple math over here, delta T1 by delta T2, delta T1 by delta T2, mass cancels, will be SH by SC. Now clearly it is mentioned the heat capacity increases with the temperature. Heat capacity increases with temperature. That means SH is higher, SC is lower. That means this ratio is more than 1. That means this ratio is more than 1 because numerator is more than the denominator. That means delta T1 is more than delta T2. So the temperature change in the colder body is more and temperature change in the hotter body is less. Meaning what? Meaning what? The object which was at 0 degrees Celsius, if you compare it with the object at 100 degrees Celsius, the change delta T1 is more, delta T2 is less. Delta T1 is more, delta T2 is less. What does this tell you? Obviously, it is not exactly at 50 mark. It is more than 50. It is more than 50 degrees Celsius. It is more than 50 degrees Celsius. So option B is correct. This was a NEET 2016 question. Such a beautiful question. I'm very good, Lone. Nice to see you after a long time. Nice to see you after a long time, guys. Is that clear, everyone, with me on this? These are the kind of questions that you will generally get in the NEET examination. Now, if you look at some of the NCERT examples, they look very scary. And if you look at the, solutions also, they look very scary. Shall we do 1 or 2 NCERT questions also? 1 or 2 questions are there and that's it. This chapter is over. After this, this chapter is in your head. You will never make mistakes unless you don't practice much problems. But understanding wise, whatever I am teaching in this lecture is more than enough. Look at this exercise 10.3 question. A sphere is placed in a vessel in boiling water. Sphere is at 100 degrees Celsius. So when you place it in boiling water, the temperature will go to 100. It is dropped in 0.14 kg calorimeter containing this much water at 20. Temperature of the water rises and attains a steady state. Calculate the specific heat capacity. Always try to divide it into 2 parts. One will be cold, one will be hot. Who is hot, who is cold, just identify. Obviously, this sphere of this mass, which is at 100 degrees Celsius, is hot and it attains a steady state temperature. This is the equilibrium temperature of 23. Question is to find the specific heat capacity of aluminium. Okay. Who is cold? Cold is 2 things. This copper and water both are at 20 degrees Celsius. They both will gain heat. This aluminium sphere will lose heat. That's all. So I will just say that the heat which is lost by aluminium will be equal to the heat which is gained by that copper and water. That's all. This is the calorimetry equation. Nothing more is required. So what is the heat lost by aluminium? Mass 0.047. Specific heat capacity only I don't know. Delta T from 100 to 23. From 100 it has come to 23. Look at this. This 23 is the equilibrium temperature. So my dear warriors, what is the change? 100 minus 23. Isn't that right? That is the left hand side. Do you know what will come on the right hand side? 2 terms, because 2 things are there, copper and water. For the copper, it will be 0.14 into specific heat capacity of copper is 385 into delta T. From 20 it went to 23. That means it is 3, correct? 3 degrees change. From 20 it went to 23. So that's 3 degrees change. Plus the water, which was 0.25 kg, had a specific heat capacity 4186. Temperature went from 20 to 23. That is 3. This is known. Here only S is unknown. Solving, you will get the value of S. All the solution, you will get 0.911 kilojoule per kg Kelvin. 0.911 kilojoule per kg Kelvin. If you don't like it like that, you can shift it and it will become 911 joule per kg Kelvin. That's the answer that you will get for aluminium. If you look at the solutions in many places and other things, you will get scared. What the hell is happening, sir? So difficult. But see, I have taught you in a very easy manner. And that's why I gave you that example of Pandu Champa. If you always look and find who is Champa, who is Pandu, and finally what is their final love story equilibrium going to look like, it's going to be very easy peasy problem. Always do that. Identify who is hot, identify who is cold, rest other things are simple. Isn't it, my dear warriors? Isn't it simple? Identifying who is Pandu, who is Champa, that's all. Okay, let's see one more example. Maybe I think I had put one more. Yeah, 10.4 example. See, I'm solving all the NCERT problems. If you say no, sir, NCERT done or not done? Done. Who? Shreyas Sir is doing it. You just have to attend Shreyas Sir's class. Other teachers may not do. Because, I know, and you know that, who is lazy? You know who is lazy? One person or a group of people are very, very lazy. Not me, not you. We are very hardworking. We do all the things. The people who make that exam, no, they are lazy. They'll directly pick previous year JEE Mains question, doom. Simple question they'll find and put it off. Oh, NCERT, okay, we'll just change this value and just put it over here. NCERT based question, okay, just put it over here. That's all they do, man. That's all that they are going to do. Okay, so the paper is actually known to you beforehand only. Just changing the values. It's very easy to get 180 out of 180 in physics if you attend all my classes. In fact, you will have to struggle to make and get very less marks. I have to make a video only. How to get less than 100 marks. That's how it is. Okay. When 0.15 kg of ice at 0 is mixed with 0.3 kg of water at 50, the resulting temperature is 6.7. Calculate the heat of fusion of ice. Identify who is Pandu, who is Champa. Identify who is Pandu, who is Champa. That's all. That's all, my dear students. Who is hot? Ice at 0. Resulting is 6.7. 50 degrees Celsius water. This is hot. Who is cold? This is cold. What is equilibrium? What is equilibrium? Resulting temperature is 6.7. That's it. So the heat lost will be equal to the heat which is gained by the cold body. So what is the heat lost by the hot body? Just see that. 0.3 kg of water, okay, into specific heat capacity of water is 4186 into delta T. From 50, it came to 6.7. So this will be 50 minus 6.7. I hope you understand why I'm writing it, because to show you this is the temperature difference by which the temperature will fall, and that's why the heat is lost. Heat gained. Now there are two terms in it. This ice first has to melt, only then it will reach 6.7. Many students I've seen, they do this mistake. 0.15 into specific heat capacity 4186 into delta T. So 6.7 minus 0. They write this. How can you write this equation? Then what will you find? All the values in LHS and RHS you know. What are you finding then? Find the latent heat of fusion is asked. So you have to add one more term. This ice has to melt, first. So 0.15 into L. That term will also come. Because first ice will melt. That's where the heat is absorbed. And then that 6 Celsius water will go to 6.7. That's when the equation is complete, and then you get the value of L. The value of L after calculation comes out 3.34 10 to the power 5 joules per kg. 3.34 into 10 to the power 5. Oops, what just happened? 3.34 into 10 to the power 5 joules per kg. That's what you get. Is that very clear, my dear warriors? Is that very clear, my dear warriors? Yes and I. Maybe in some different units you will get 0.3. But yeah, this is how you do it. Always identify Pandu Champa, see what the equilibrium is, or if it is not given, you identify or assume it to be T and then solve it. That's all that is there in these kind of questions. It's very simple. Now, please remember, you have to be a part of Telegram group, and you have to share whatever we are sharing on Telegram to your mutual Telegram groups. Share. it from our Telegram groups. Let others also know that there is something amazing happening for all the students who want to learn in English. And this is the biggest English community, my dear warriors, in entire country. And thank you for making it 147k subscribers. Let's go soon to 150k subscribers. So daily schedule you will get. You'll get daily quizzes, right? You will get flashcards and other important materials. You will get notes and you will get mock test links which are conducted every week. All of this in the Telegram. Make sure you are a part of it. This Sunday also there is going to be a mock test. Ranks will be displayed. Marks will come. You can compete. It's absolutely free of cost. You get to experience at home. Why do you want to pay thousands of rupees and enroll into some random test series with errors? Join the Vedantu test series. And if you have watched the lecture till the end, please put up my I am hot. I feel that this is relevant here. We studied thermal physics, thermal expansion, heat, temperature, becoming hot. So put it up. I am hot. Doesn't matter. I want everybody to put it up in the comments after the session is over. So I know you have watched the lecture till the end. And yes, this was your Captain Shreyas. This was my introduction slide. I always put it up in the end these days because I don't know. I think people know me. So I thought, okay, fine, we can just put it over here. Anyways, so smash the like button. Thank you for subscribing and have a great night. It was lovely chatting and, dealing with all these concepts in the night. It was a fun session. Thank you so much. See you. See all the hot guys and girls in the comment section. Bye-bye. Hasta la vista, Captain Shreyas signing off.